because it's relevant for the systems. And one thing that in principle I'm not going to cover in this session is a statistical machine translation in this unsupervised setting, because for that I would need to explain quite in detail statistical machine translation, and I will not do it in these sessions, but at the end, in the last session, we will have the state-of-the-art system, the one that performs best in WMT. And if this kind of systems is one of the winning, I will go back there and we will talk for some time about this system. But this is something that I'm not intend to cover today. Some references that we can use for this. You will see that I will be referring to specific papers during this webinar today, but I recommend a couple of references that I have also used to prepare this talk. One is a tutorial that was given a couple of years ago on cross-lingual embeddings by Sebastian Roder, Anders Sogar, and Ivan Gulic. It has more information than the ones that I will be giving today. So if I will be talking about 40 minutes on this topic, the tutorial covers 3 hours. So yeah, you can get more examples and more understanding there. And also another thing that is very informative is Mikel Artech's thesis that goes completely on supervised machine translation. So there are a lot of examples and lots of experiments there. It's worth having a look. And then also something that goes a bit beyond what we will talk in today is a tutorial that was given recently at EACL on advances and challenges of unsupervised neural machine translation. And there you can see experiments and examples of learning together these cross-lingual embeddings and supervised MT, and also how multilinguality can help supervised MT. And I will say the same that I said with the statistical unsupervised machine translation before. If we see that it's at WMT competitions, these are the top performing systems, I will go back at the end of the webinars and we can talk about these systems then. Okay, so yeah, let's start because there are lots of topics to cover today. But I would like to start first with a short recap of what we saw in the first session and how it relates to the things that we are doing today. So the first day, what we did is talk about low resource NLP, and I define it like something. Low resource setting is a scenario where we cannot use standard NLP techniques because they perform very bad. And we saw that a low resource setting is not something that it's easier to define because it depends on the task, it depends on the language that you're considering, it depends on the domain. So it depends on several things that go beyond the amount of data that you have, which of course it's also important to define a low resource setting. And we saw this in an example. We talk about the machine translation of languages in the Americas. And that was a shared task that was aiming to have good translation quality for several languages in the Americas. But all these languages had very few data for training. We have around 4,000 parallel sentences for some languages like Ashakanimka, and then we have like 125,000 sentences for Quechua. In the middle, we have like 9,000 sentences for Wixárika. And this was an example to see that the amount of data is not strictly related to a low resource setting, because when we try to see what was happening with the languages, we saw that the best performing system at the end was the one that was trying to translate Wixárika with a BLEU score of almost 16. And on the other hand, for Quechua with 15 times more data, the translation quality measured by BLEU was 3 times smaller. So this is an example where the amount of data is not the key point to see the low resource setting, but in this case, for instance, it was very important, the difference between languages, the the complexity of the languages involved. Another thing that we saw the other day is that there are different approaches to perform low resource natural language processing. I did this division in 4 groups, the one that deals with data, another one with machine learning solution, then using multilinguality or multimodality to increase the resources, or devising specialized architecture for your problem in question. So yeah, today we are talking about unsupervised neural machine translation. This in general belongs to the 4th classes here. It's a specialized architecture to deal with one problem. You don't have parallel data, only monolingual. So you design a new architecture to deal with this. But of course, it also belongs to this general machine learning class because it's an unsupervised technique. And we will see in the next seminars where it can be also approached as a transfer learning approach. But also it uses some data augmentation techniques. At the beginning, I said that we will be having a back translation module, and this is one of the data augmentation techniques that we use in machine translation. So at the end, we have one problem and we use several different techniques to work with this. And this is something that we saw also the first day. We were talking about Yoruba English, that this is an example that I'm giving several times because we have been working on this language pair. And we saw that we could approach the problem with different techniques. We could do domain adaptation, we could do pre-training with from large models, we could do task adaptation, we were using multilinguality there, and we saw that different techniques work best in different problems. So for instance, going into English, multilinguality was a very good way to go. But for going into Yoruba, where we have less data, domain adaptation via transfer learning was the best approach. So at the end, the technique that you use depends on the problem that you have. And you cannot generalize and saying that this is the best way to work on low resource natural language processing. It really depends on the project that you are trying to approach. And this is a summary in just 5 minutes of what we did last time. So let's start with today's topic, that is unsupervised machine translation. And as we said, the main ingredient of unsupervised machine translation can be cross-lingual embeddings. And I'm not going to talk about word embeddings a lot. This is something that I already skipped the first day, but there are things that are relevant here that I'm sure that all of us already know. For instance, a word embeddings is just a numerical representation of words that allows us to do mathematical operations on words. And besides that, these representations have very nice properties that talks about semantics and morphology of words. This is the typical example that is given for word embeddings. The fact that if you subtract man to kin and add woman, what you obtain is the word queen. So this shows how semantics is reflected in word embedding. So in these spaces, gender information can be recovered just moving with a linear transformation from one word to another. And it's not only semantics, we also see morphology, like in the example that we have on the right? So if we have the direction that goes from king into the plural kings, we observe that we have exactly the same direction when we go from queen into the plural queens. So both semantics and morphology seem to be reflected in word embeddings. There are really lots of types of embeddings, and they were used in neural networks since some years ago when word2vec was starting to get impressive results in several tasks. But word2vec is not the only way you get to estimate embeddings. For word2vec, we already had several other estimations for embeddings. The more simple ones based on term frequency or TF-IDF, but also more sophisticated embeddings that one can estimate on co-occurrences matrices. And these embeddings also would give quite a good performance. But as I said, the big jump in quality came with the prediction-based embeddings, where we have word2vec architecture like Skitgram or CBOW, and also we have GLOBE, that it's a combination with these co-occurrence matrix things and prediction-based embeddings. And also we can have different kind of embeddings using the same architecture, depending on the basic unit that we use. So we have standard word embeddings with word2vec or WOC, but we also can have the reflection of how engrams influence in each of these embeddings. This is one fast text tags, for instance. We can have the influence of each character independently in character word embeddings. There are different ways to obtain the embeddings that depend both on the architecture and on the basic unit that you use for these embeddings. Another thing that will be useful later for us is to know how can we evaluate the quality of word embeddings. So there are mainly two big methodologies to evaluate embeddings. This is the extrinsic methods and the intrinsic methods. Extrinsic methods are easy. You just estimate your embeddings and use them in a downstream natural language processing task. So if you want to do name entity recognition, you initialize your models with word embeddings and you can see how they improve or not your name entity recognition tasks, or a classification task, or part of a stitch tagging, or whatever. On the other hand, we had these intrinsic methods. Intrinsic methods in a way, because this is also an NLP task that you want to improve your quality. So, and this is mostly the task of saying what is the semantic similarity within several words or word analogy. So the example that we have before, man minus king equals to woman, and we want to find king. This would be an example of word analogy. For this, we have several test sets that have been manually annotated with the similarity of the words, and then we just correlate the results of our word embeddings with this human annotation. One interesting thing to notice is that these two big methods don't correlate among themselves. So the best embedding for your downstream NLP task cannot be the best embedding that you are getting when you evaluate word analogy. So this is also a thing to notice. So the best word embedding architecture, the best word embedding basic unit depends on your final task. And here we are worried about the low resource setting. So which things do we need to consider in the low resource setting? So the first thing is that if you have few data, the quality of your embeddings will be worse. So if you train word2vec with millions of tokens, it's not going to be the same as if you train word2vec just with thousands of tokens there. So the amount of data clearly affects the quality of your embeddings, but also the noise in the data that you have. If you have very noisy data, the embeddings will be able to capture less semantic information. Also very important to take into account, especially in the low resource setting, is that if you have a domain mismatch between your training data and your final task, the quality of the embeddings will be also very, very bad. So if you are training data on Wikipedia, but then what you want to do is to train a name entity recognizer on news, it probably will fail because it will lack a lot of information. Also, in the low resource setting, it's more important the architecture that you are trying to use. So because you have less data, you have to take most of it. So sometimes the difference between using a SIBO or GLOBE, for instance, can be quite big. So it's very useful. Try to use very different embeddings. They are very cheap to obtain and they train very fast. So in your system, it's very good just to try different architectures and see which is the best for your system. And another difficulty that we faced in the low resource setting is that embeddings are difficult to evaluate, because I showed you before that we have two kinds of ways to evaluate, this intrinsic and this extrinsic way of evaluating embeddings. But for instance, for the intrinsic evaluation, you have, I don't know, like 20 test sets to evaluate in English, but then you go to a low resource language and you don't have any. So the first task to do is to create your own test set, either translating from English or not, and then you are able to evaluate the quality that you are getting. So even the evaluation is difficult in the low resource setting. And let me give you an example of all this. Again, and we'll be using Yoruba because, yeah, I said that we are working on this language in the group. And in this case, we did experiments on word embeddings for Yoruba and Twi, that are two languages that are spoken in Africa. They have differences, of course, but one of the differences is the amount of data that you can gather for it. Twi is more low resource in this sense, so we were able to obtain less data. This is a table of all the data that we could gather for Yoruba and Twi. And there is a column here called status, when native speakers of the language look at the data that they collected and tag the data as clean or noisy. As you see, for Yoruba, there is quite a big amount of data here that is tagged as clean. In particular, if we look at JW300, we look at this because this is a huge corpus that is in several languages. We see that we have more than 10 million tokens that are clean enough and can be used to obtain nice embeddings or to be used to other NLP tasks. We go to Twi. We also have JW300, but we see that in this case that the corpus is noisy. Noisy for these two languages in most cases refers to diacritics, because both languages have a very high dependence on diacritics, and it's difficult to have a proper diacritization and some of the text. Another thing I want to notice here is that in both cases, the corpus that we have and we found it's quite clean is the Bible. So the Bible is a resource available in lots of languages that it's very clean and ready to be used. And then another thing I want to notice is that another corpus that we have in both cases is Wikipedia. We have Wikipedia here for Yoruba and Twi, but notice that it's noisy in two cases. So this is Wikipedia is a corpus that is in more than 200 languages, so it's used for lots of NLP tasks, especially for training this huge unsupervised model that we will be talking later. But and it is assumed to be a clean corpus and a kind of polite data. But when you look for low resource languages and you look a bit, you see, for example, that in the case of Yoruba and Twi, this data is noisy and it's going to perform bad in some tasks. The experiments that we did here is to see the effect that all this had on word embeddings. And the first problem that we had is that there was no test set to evaluate. So the first thing to do was to create this test set. So we took one of them, this WordSim 353, that measures the correlation with human judgments for the word similarity task. It was translated manually by native speakers, and we use the same human judgments that in the English one. So this had to be taken into account because there are some pairs that cannot be translated in another language. So the test set has to be slightly different in any language. So we train fastest embeddings on the corpus that we have seen before with different partitions. And what we also did is we used the pre-trained embeddings that are available for Yoruba and Twi. These pre-trained embeddings on fasttext are given by Facebook, and they were trained either on Wikipedia alone. This is this F1 that I have here, this pre-trained model wiki, or in a combination of data that Wikipedia and Common Crawl. This is this F2 that I have here. All of this with fastest embeddings. And the first thing that we see is that for Twi, for instance, these pre-trained embeddings that are available have a very tiny vocabulary size, so less than 1,000 words are covered by these pre-trained embeddings. There is no common crawl on Twi, so the only thing that one can get is this Wikipedia model. For Yoruba, it's a bit better regarding to size. And we see that with Wikipedia, the size of the vocabulary increases to 21,000. And if we add common crawl, it increases to 150,000 words. This is starting to be a significant vocabulary. But if you look at the correlation with human judgment, you see that the performance is terrible. So with this pre-trained model, the correlation, the Spearman correlation with human judgments on this task of word similarity is of order 1.1. So there is almost no correlation with human judgments. And in the case of Yoruba, when we have the small and the big model, the more vocabulary that you add, the worse is the result. So you get below 0.1 when you increase your model. And this is related to the thing that we were talking before. When data is not clean, the quality of the embeddings is even worse. Below, in the second part of the table, we can see the effect of our data. So we had this distinction on small and big data and noisy and clean data. And what we do is train two different embeddings with different amount of data and quality. And what we observe is that using clean data, even if it's a small data set, already improves a lot the performance. We can see in Twi, this is not clear because we already, even with our small data set, we have 10 times more vocabulary than in the pre-trained models. But if you look at Yoruba experiments, we see that with half of the vocabulary, we are able to double the quality measured as Spearman correlation with human judgments. And adding more data to this clean data is not always good. For Twi, for instance, we can have four times more vocabulary, but then the quality only improves a tiny bit. And similarly happens for Yoruba. We get a bit of improvement with all the data. We get like 4 more vocabulary size, but then the quality is improving only relatively because the data that we are adding is noisy in this case. And yeah, and this will be used later to see how the quality of embeddings is relevant when we want to use them for cross-lingual word embeddings, because cross-lingual word embeddings will be based on having high quality word embeddings. So yeah, the first task is to be able to get high quality monolingual embeddings, or at least you do your best with the data and architectures that you have. This is what relates to monolingual semantics of word embeddings, but another very nice property of word embeddings is that if you manage to get bilingual embeddings, that means that you have embeddings in 2 or more languages simultaneously and can put them on the same space, you see that the same word in 2 different languages stays very, very close together. This is an example of bilingual embeddings in German and English. And you see that on the right-hand side, we have, for example, interest and interests that are almost overlapping in the space. And the same happened with peace and freedom, children and kinder, several examples. So the same word in different languages lies together in the same space when you are able to get these bilingual embeddings. And our job now is being able to know how do we really get this bilingualism? How can we project or obtain embeddings of different languages in a same space? And when you read some literature on the topic, you will find really lots of approaches that deal with this. And these are named, the same approach can be named under cross-lingual embeddings, bilingual embeddings, or multilingual embeddings. At the end, all of them refer to the same thing with very few variations. So this was just a very big summary of word embeddings, just with a few slides. And let's go to see this bilingualism. How do we get to cross-lingual embeddings? I will be talking about cross-lingual embeddings during the next slide. First, and the first thing to know is that we can divide these methodologies into kinds, as with most of the tasks in machine learning. You can do it in a supervised way or in an unsupervised way. And inside unsupervised methodologies, we can do joint learning or we can do mapping. So in joint learning, you're trying to learn the embeddings simultaneously in all the languages. In mapping approaches, what you do is you get your monolingual embeddings and then try to put it together as a post-hoc alignment. And this will be very much related to unsupervised word embeddings, because this mapping is the key for getting these embeddings in an unsupervised way. And we will see that we can do it using either self-learning or adversarial learning to get similar results. But why are we really interested in doing this? First, because we have seen the nice properties that have monolingual embedding. So if we can get the same in a cross-lingual setting, we can model the meaning in a multilingual way. And this is really very useful for multilingual NLP application and for giving support to cross-linguality in several things, from question answering to dialogue to machine translation to path-to-speech tagging, whatever NLP task you can think of. Monolingual, if you have good quality multilingual embeddings, you can try to do transfer lengthening or adapt in the multilingual setting. And why should we go with supervised cross-lingual embeddings? First, because we will see that they are quite simple. And because even if they require supervision, some kind of supervision is most of the time possible, because there are very complicated approaches we will see now, but then we also have very simple approaches that only need a small dictionary. As by a small dictionary, it might mean 20 words. So at the end, this is something that one can easily get for several language pairs. And then why do we have the reason for going unsupervised? First, because there might be cases when these dictionaries, even small, are not possible, very distant languages with very few speakers or very far from your expertise. And also quite important because unsupervised embeddings are sometimes or better quality than supervised embeddings. So yeah, if you get better quality in the unsupervised way, so yeah, there is no reason to do the supervised version. But even this quality is something that we can discuss a bit later. What's better, supervision or unsupervised embeddings there? So let me start with the summary of these approaches. And this area of research has been very active, let's say, in the last 5 years. So it's impossible to me to give a comprehensive description here. And so there is no time, and I don't know all the papers that have been written here. So what I will be doing is focusing all the explanation to our understanding unsupervised neural machine translation. And that will mainly mean talking about unsupervised word embeddings and self-learning. And these methods are also very used in several low result NLP tasks. So I will put examples of machine translation, but everything that I'm saying here is general for any low result setting that you may have. And from the references that I've said at the beginning, some of the things that I will be explaining now are taken from tutorials by Sebastian Roders and his blog. So yeah, don't miss them if you don't understand something here. I'm sure there you can also find nice examples and an explanation. So there are lots of ways to obtain supervised cross-lingual embeddings. And the main difference between all these ways is the kind of supervision that you have to do the learning. So you can have supervision on word level. In this case, what you need is either bilingual dictionaries or word alignments between sentences or whatever can give you these bilingual dictionaries. You can also have methods that work at sentence level. And in this case, what you need is either parallel corpora, the same that you would use for machine translation, or documents when you can have sentence alignment. And finally, you also have methods when what you use is comparable corpora or documents aligned. Also crawl web pages where you have some information that which documents are related to which document in another languages. And here below, it's just the name of 4 of the best performing approaches for supervised cross-lingual embeddings. As you see below in the reference, this is from a paper in 2016. So you see that the topic is already quite important for the last 5 years. So we have 4 examples here. The first one is the extension of the scriptgram to the bilingual setting, that's bilingual scriptgram. And in this case, this is quite an expensive method because what it needs is word alignment. So in this case, they were using parallel sentence with word alignments. Slightly cheaper, we have this also bilingual CVM, when what you have here is sentence aligned data, so the same data that one used for machine translation. Then we have this bilingual CCA. In this case, what we would need is a bilingual dictionary, so a bit cheaper to obtain. And finally, another example shown here is this bilingual BCD that it uses comparable documents to learn the alignments and learn the embeddings together. Let me just generalize a bit what all these models have. These models kind of do the same training and we would do for in the monolingual setting. This is represented by this neural network here that tries to represent a skip graph model. We would have the loss function for this source language here. We would have the same skigram model here with the loss function for the target language. And the novelty is that the complete loss function will also have a term that depends on both source and target simultaneously. And this is what is acting as a cross-lingual regularization and what helps the embeddings to be learned together and to lie in the same space. It's only when they lie in the same space that we can do this nice comparison that we have seen in bilingualism before. So how do these models work? Well, it depends on the concrete model. Let me give the ones that I think that are more relevant here, or at least they were important when they appeared. The first one was this bilingual skigram, what we have seen before. This is just an extension of the skigram that we have before. In a skigram, you have one word and your task for learning is predicting the context. So in the bilingual case, we are doing the same. We have one word, but you need to predict at the same time the context in the source language and also predict the aligned words in the target language. So we are predicting the 2 contexts simultaneously. This is direct because at the end, this is skigram, it's exactly the same, but it's expensive because for this you need parallel corpora because you need the same sentence in 2 languages. And you also need the word alignments to be able to have this correspondency between the two languages. These word alignments can be automatically obtained. You can use fast text or whatever, or this or whatever, but still you need a parallel corpus for them. And as we can see before, with a small parallel corpus, we will get a lower quality embedding. So the parallel corpus needs to be big to be able to get a high quality embeddings. This is not the only way to do it. There are different ways that try to ease things and make it cheaper. So a couple of years later, no, this was I think the same year at the one before, there is an extension also to a skip-gram model where they try to do the same but without word alignments. And in order to do this, what they do is just assume that every word in the source language is uniformly aligned to every word in the target language. And then there are a couple of methods that you see that do this. Bilboa and then the transgram method that differ on the way that they calculate the distance between the languages. But the idea here is exactly the same. You have your global architecture that has a component in the loss function for the source language, another for the target language, and then a component that is taking care of the multilinguality here. Let's see also a bit different model. In this case, this is not an extension of a skip-gram, but a kind of extension of GLOBE. And the difference here is that we are not taking only this prediction-based approach that takes care of frequencies in your context, but it's only taking co-occurrences matrices here. So no need to go a lot into the details here, but the idea is the same. We will have the monolingual GLOBE losses, and to this loss we will try to minimize also the distances between the two languages. Again, this is quite an expensive approach because we still need to have parallel corpora and word alignments, and also the authors were using SMT probabilities, statistical machine probabilities coming from phase tables, in order to be able to weight the alignments in the two languages. So this is again quite an expensive approach in resources. So we need again big bilingual corpus. And this is just a selection of supervised embeddings that I learned jointly for the two languages. But then we have another big family of models that what they do is project monolingual embeddings. And in this case, we would have monolingual embeddings in the two languages. This is a representation of English and Spanish. And we want to do is a projection in a common space. You can do several things. You have two monolingual embeddings and project them in a single space, or you have one monolingual embeddings and the source embeddings and project the target into the source, or you can do the opposite, project the source into the target, or whatever combinations that you can think of. The things that all the methods have in common is that you need to learn a projection matrix. And what assumptions do you need to take to do that? Okay, so the fact that you can project embeddings mean that the embeddings have to be similar, right? Because if you have embeddings that behave in one way in English and embeddings that behave in another way in Spanish, there is no way that you can project them and share properties. You need that monolingually these languages share properties. And this is one of the main assumptions that we have in the cross-lingual setting. We will be assuming all the day and the days after that isomorphism holds. What does it mean? In the sample here, this is a picture taken from one of the best architectures for learning cross-lingual embedding. This is from a paper by Kono and Lampert at the beginning of 2017. And we see in the left part of the plot that we have a space for English. This would be the word embeddings for English, this X, and then we have a space Y for Italian. So, and the assumption here is that if you somehow modify your space X, somehow you will be able to put it in on top of Y and be quite similar. So you are, as you see in this picture here, you are not deforming your space, you are kind of rotating, translating that. This is starting to sound like a linear transformation, right? You see like a rotation and a translation here. So you must assume that spaces are isomorphic, they have a similar structure, so that you can apply a transformation and convert one into the other, and only in this way they are comparable. Another thing that we can assume, and we will be assuming a bit later, is that the similarity inside a language is something that is general between languages. So what do I mean? For instance, in this plot here, this is from the other big approach to unsupervised embedding, the one by Arteche and his team. That what he was saying is, okay, let's assume that we have the English word to, and we try to observe how to relates to all the other words in English, and we just plot the distribution. So how to relates to the word three, how to relates to the word cat, how to relates to the word deep, and we write this distribution. And then we do the same in Italian. So in Italian, we have the word due to say two, and then we look at the distribution. And what we would expect is that the distribution between tu and due is quite similar because we are referring to the same semantic concept. And if we look for another word, in this example, they look at the word dog, the distribution between this word and all the other words in the same language will be different. So this is another assumption that is quite important and will be used as a heuristic in some of their projects. But the main thing for all cross-lingual embeddings is that behind we have the assumption of isomorphism, and we have to take into account that this might not be true. It's an assumption that we are doing right now. Okay, so yeah, we know the basics, and now what we want to do is to find this projection. There are several ways to do this, and the most easier way to do it is just minimizing the Euclidean distance. So we have our embeddings in one language, this X, we have our embeddings in the other language, this Y, and remember that we are in a supervised setting, so we can assume that we have a dictionary. So by mapping the words in this dictionary, we can find this matrix W, then that's the projection between the two spaces. This was the basic first approach, and there was some criticism and kind of improvements that were coming slowly later. One of relevant things came a couple of years later by Ching et al., saying that, yeah, that to do this, you were trying to minimize the Euclidean distance, but then when you do your estimations for evaluation, you are using cosine distance. So this kind of mismatch was damaging performance. Also that if you don't prepare well your embeddings, and by preparing, I mean like Unix centering, normalization, so that they are really comparable, it's difficult to match the two species properly. So these ones were some criticisms to the first minimization of Euclidean distance, and all these kind of improvements were reflected on the quality of the final embeddings. And another thing to be noticed is that, yeah, if we go to this minimization of Euclidean distance, we are not saying anything about the nature of W. So W can be anything. And if W can be anything, mathematically, we don't have a closed form solution. This is not really a very important problem because you can solve that equation numerically. But yeah, but the people notice that if you impose some restriction of W, it would have a closed solution. It's nicer, it's very elegant, and the training is also faster. You are not using any a numerical approximation there. And also what was also relevant is that if you also force the W to be orthogonal, you obtain better results than if you are not imposing orthogonality. And this is related to the example that I showed you in the first slide. So if you see this example here of the Italian and the English examples, what people were doing here is just rotating and translating one space. That's a linear transformation that it's one of the orthogonality properties. So if we see that orthogonality is beneficial, so we try to impose that W is orthogonal to get our cross-lingual embedding. And that's nothing else than the Procruste's problem. Procruste's problem, what tries to solve is this obtention of the best matrix that is able to project one space into the other. And this is very simple to remember. Procrustes was a bandit in the ancient Greek in Attica who had an inn there, and the travelers that were around and stay in his inn has some problem, because Procrustes, what he was trying to do is fit them in his bed, and the bed was always either too short or too long. So he was trying to fit the travelers into his bed, and if they were too long, he was just cutting the legs and arms. If they were too short, he was stretching the travelers. So this is exactly what we want to do with our embeddings. We have our embeddings in the source language is we can say is the bed. Our embeddings in the target languages, we can say is the poor traveler that Procrustes found. And what Procrustes wanted to do is just modify the traveler so that it fits the best as possible the bed. So this is what the Procrustes problem is trying to solve. The solution is very, very nice and elegant here, but it's not, I'm not going to show it here, but it's very simple. What we want to do here is to find the orthogonal matrix that closely maps the two spaces. So we are trying to minimize the Frobenius norm that you see here in the slide, subject to this orthogonality constraint. And the orthogonality constraint just means that the product or W with its transport is the identity matrix. And in that case, W with give us the optimal rotation, reflection, and translation matrix. And it can be shown that the best W can be just found just by a simple SVD. So if you do some singular value decomposition of your product of matrix of the source and target embeddings, you get two matrices U and Phi and V, and the product of these matrices are just the projection that you are looking for. So yeah, I think I've done several digression now. Remember, where are we? We are trying to get cross-lingual embeddings in a supervised way. So what we have is monolingual embeddings, let's say Word2Vec, Globe, FastTech, or whatever. We are in a supervised setting, so we have a dictionary, some parallel data to use. We want to find the best projection matrix, and we have seen that to do this, we just need to solve the Procrustes problem. And now, after this solution, we will have W. And with W, given a word in one language, we would apply this matrix to be able to obtain the word in the other language. What can we do to this? So we could just look for the nearest neighbors in the other language, and you find the closest one to your original word. To measure distance and similarity, you need a measure that's, for instance, cosine. So in principle, the word with a higher cosine similarity in your target language would be the one that would be mapped in your source language. So yeah, that works, but we can still do a bit better. So this is the general way we have to get cross-lingual embeddings, but still we can notice some problems of embeddings, what is called the hipness problem. This hipness problem is not something specifically related to embeddings. It's related to any high dimensional space. So when you have entities in a space with a lot of dimensions, and we can say, I don't know, our regular space has 3 dimensions, our physical space, but when we go to word embeddings, a number of dimensions that we typically use can be 300 dimensions for word embeddings. If you go in a machine translation system, the embeddings there can have 500 or 700 dimensions. For classification tasks, you can be using embeddings with 50 dimensions, for instance. So we are, in all cases, we are in high dimensional spaces. So in general, one observes that in these spaces, a small set of vectors are neighbors of a huge amount of target vectors. So we have some hoops. So there are words that are close to everything. And this is not related to language itself, as I say, it's related to a high dimensional space. The analysis was done in 2015, the first analysis by Dino et al. And I give you here an example of some of the hubs that they found in English data. And I'm showing this as just to say that to show that it's not related at all with languages, because if you expect some words to be clustered of a lot of words in the other language, the first thing I would think of would be prepositions, for instance. The preposition D in my mind would be very close to lots of other words. But if you see what's happening, it's not a preposition or stop words of whatever. There are some words that for some reasons they are hubs, and the reason is just the structure of the space. In this English Italian, the word that has a higher hipness measure was Blogmontov, that I don't really know either the meaning. And then we have a couple of dates, we have communals, limassol, that we have a conjunction, and that would make more sense linguistically, but you see that it's probably random. And the hubs are really a mathematical artifact in this case. And of course, when you want to do projection in one language into the other, you want to avoid this. Because if you have words that are very close to lots of other words, there is a lot of chances that these words appear as translation as a first option. In the same word, they gave some example of this. For instance, in Italian English, one of the hubs was, for instance, Dio, and that means God in Italian. So when they were trying to get the nearest neighbor for Almighty, in English, that should be omnipotente in Italian, one tenth form is Dio, because the hub of this word was very high, so it was in the top list of the nearest neighbors ranking. So, and it's a very it's a word that would appear a lot of times in your dictionary, in your data, so the frequency is high, so the translation, the embedding quality would be good. So it has a lot of possibilities of appearing as translation. And the same with other examples. They have here, for instance, backwardness, that should be arretratezza in Italian, but the translation again was another hub, this date here, which has really nothing to do with your input. So solving these hubness problems seem also to be a relevant thing to do in your translingual embedding settings. How do we do that? Again, there is never one single solution. There are several solutions that can be applied here. I will just talk about how we can rescale cosine similarity in order to get rid of these hubs. And this is mainly by using margin-based similarity. If we, for for getting the closest word to another word, we will usually use cosine similarity. So we will estimate the cosine within the source word in language 1 and the target word in language 2. So the thing that we want to do now is just to discount some weight to this cosine similarity that takes into account how dense are the regions near this word. And to do this, we just take the average of cosine similarity of the nearest neighbors. So this is what you have here below, the average similarity. You do this in your source part, you do this in your target part, and you discount it from the cosine similarity. And this measure in this way is called cross-domain similarity local scaling. It was introduced in this Conot and Lampe paper that I told you before, and is used in several approaches to try to get rid of this hardness problem. It's not the only measure. A bit later, Artechen and Sven just kind of generalized the issue and realized that it's not only a subtraction what you can do several operations to rescale the cosine. And in their case, they found that the best thing to do was the ratio between the cosine and these average similarities. And I put here laser because this is something that we will see also later, that the main architecture called laser is using this margin-based similarity here. Where are we? Again, yeah, we are finally done for our supervised cross-lingual embeddings. We have our monolingual embeddings. We know how to get as good quality as we can. We had a dictionary to do the supervision of the projection. We know that we need to solve the Procrustes problem because it's the way that we have to find the mapping between the two spaces, assuming isomorphism. And we know that we should be using a margin-based similarity to be able to find translations from one word in one language into the other language using this cross-lingual space. And with this, we have covered supervised methods for cross-lingual embeddings, both the joint learning and mapping approaches. So yeah, there are two methods that are quite different. Which one should be used? Well, it depends. I mean, both of them are good. In some cases, you might prefer one or the other because you have more or less data. So we have seen that joint learning approaches need a lot of parallel data in any way. For mapping approaches, you need dictionaries and they can be really small. So in that sense, mapping approaches should be appear to be a bit better because they need less supervision. But in other hand, the assumption of isomorphism is stronger in these mapping approaches. It doesn't mean that it's not there in joint learning approaches, but it's very important in mapping approaches. And there have been several works that say that this isomorphism really doesn't hold. And the fact that it holds or not, it depends on the language pair. It's more difficult when language pairs are very distant. It depends on the training corpora. If training corpora, it's about different domains. It's more difficult to have some isomorphism there. And it also depends on the algorithm that you use. If you try to map a word to back to a globe embedding, it's not going to work at all. You need to use the same architecture and an architecture that makes sense to your problem. And there are several works that analyze this. I cite here the one by Sogard, Patra, and Nakascol and Flauber that were done like 2-3 years ago. As I said, both methods have drawbacks and good things. But let's try to compare them as a first setting. And a first setting would be one when we use exactly the same amount of parallel data in both. So if we can do joint learning using a parallel corpus, let's see what we can get using the same parallel data to train embeddings monolingually and then map them. And what we see several things in this paper, in this table, sorry. The first column is the eigenvalue similarity. And this is a measure of isomorphism. The lower the value it is, the more isomorphic are the spaces that you get. And we see that in all cases, joint learning is able to get lower eigenvalue similarity. So isomorphism is better reflected by joint learning than by mapping. And this is very clear when languages are distant. The example that we have on the top is Finnish English. So languages are far from each other. So joint learning really achieve better isomorphism between spaces. We go to more similar languages. We have the third one, for instance, is German English. And we see that this measure is closer. So we have 33 versus 39, but before we had like 28 versus 115. So the nature of the language pair is really very important to be able to say we have isomorphism or not. Then we have a measure of the hardness, the problem that we are trying to solve with these margin-based measures. And we see in this case, the higher the measure, that means the less hardness, so the better for your approach. And we see also, if we look by far the table, that all the black numbers correspond to joint learning. So we get less hardness when we learn the embeddings via joint learning. If we compare the cosine, the basic cosine approach, this NN here, to the margin-based measure, this CSLS here, we see that CLS here is slightly better than cosine. The difference is not as big as with the eigenvalue similarity, but still using this margin-based metrics improves the results. And finally, let's see the translation accuracy that we get with both embedding approaches. So again, all the black numbers that you can see are obtained using joint learning. So sometimes the difference is very small. For instance, Spanish English, we have just a couple of points of accuracy. And if you go to very distant languages, and the difference is really huge. So we have 30 points of difference for Finnish English. And this is because our assumption of isomorphism is not holding in this space. So this is something to take into account. Under the same conditions, probably one would use joint learning approaches, but you really cannot use them always because you don't have just the data to train them. So mapping approaches are easier to transform because they need really very few supervision. But now, then you need to find clever ways to solve the isomorphism assumptions. And this is where current research is putting a lot of efforts now. How can we make languages that are so different to be able to fulfill this isomorphism demands that you need for mapping spaces? Okay, so yeah, this is the ideas that I wanted you to get about supervised cross-lingual embeddings. And the step from supervised to unsupervised embeddings is really very direct, because we have already done the hardest part, trying to understand this mapping approach. So the step from mapping supervised embeddings to mapping with self-learning and supervised embeddings is really very direct. So what we do with this self-learning approach is very simple. At least the idea is very simple. We have these two embeddings in two different languages. We have a small dictionary that acts as anchor pair to do the mapping. And with this small dictionary, we do the mapping. And we do this thing several times. So once you have your first dictionary, you can map, you can learn this W. Now you have a W that is good and allows you to get more anchor pairs. So you have a larger dictionary or a better dictionary. So you can do the mapping again. And now your W will be better, and then we will get a better dictionary. And this iteratively till you are happy with it and you have your final merged embedding space to get these cross-lingual embeddings. This is what we have been doing in the supervised way. So yeah, this is one slide from the thesis of Miquel Arteche. And what's the difference between the supervised and the unsupervised setting? In the supervised setting, we will having a dictionary. And with this dictionary, we will starting with this iterative process. In the unsupervised system, we don't have this dictionary. So what we need to do is to induce this system. And this is the only difference. We will have an additional step when we try to induce this dictionary. It's also quite interesting to know the relevance of the dictionary. Which side do we really need? So this is an experiment when they try to see the accuracy by changing the size of the dictionary. The largest dictionary that they had was 5,000 words. And this is the thing that used Mikolov in the first paper in 2013 to get a bilingual mapping. And then they were decreasing the size of the dictionary till 25. And 25 is this purple line here. And you see that after 40 iterations, the results are not that bad. And if you go to just 50 parallel words, you get an accuracy that it's almost the same that you get with 5,000 words. So the size of the dictionary shouldn't really stop you, because with very few things you can get high quality results, or at least as good results as you would get with larger dictionaries. Also notice that there is a line here, numerals. This is the dashed line here that gets a very good performance. And this is just a very simple approach for languages sharing the same alphabet. Just match the numbers. Numbers can be used as words, as anchor points. And the same happens with cognates. So anything that can be matched can be used as a dictionary here, and it performs quite well. So where are we now again? So we are in the same setting as before, as with cross-lingual supervised embeddings. And what we want to do here is we will want to induce a seed lexicon so that we can start our method. And in order to induce this lexicon, again, we have the problem when we need to assume that both spaces are isomorphic, because you cannot match two words if they are not behaving the same way, right? We have just seen that. And then we just do a mapping. We learn a projection W again on this dictionary. This projection is assuming isomorphism again. And with this new projection matrix, we can induce a new dictionary, and we go again to the mapping phase. How can we induce the seed lexicon? You can use adversarial learning for this. You can try to envisage some heuristics that happen in your space. That, as example, in the distribution with dog and 2 that I showed you before, you can do PCA, you can solve an optimal transport problem, lots of ways to induce an initial bilingual dictionary. In the next slide, I will talk about similarity of monolingual similarity distribution, the example with the dog and the 2, and adversarial training, because this is exactly what we were looking at, what we will look at with the unsupervised machine translation. And the other things we already know. So we know how to do the mapping, that was solving our Procrustes problem, and we know how to induce a new dictionary, because that was using a margin-based similarity to map one language into the other. A comment to notice also here, the importance of processing pre and post the mapping. So we have seen at the beginning what we wanted to do: unit-line normalization, mean centering, everything that I have said before at the beginning with supervised settings is also very important here. It's even more important here. So for this method, they do a very strong processing before and after mapping. They do normalization, they do whitening, that is, they use the covariance matrix, they convert them into the identity matrix. And after the projection, they reweight each component according to the correlation. They whiten again if they have been using whitening in the pre-mapping, and they reduce the dimensionality of the final embedding. So if they are working with 300 components, in order to get the new dictionary, they only use the top K components, because they are supposed to be better for the mapping. And the specific processing depends on the method, but in all the cases that it's important that something to clean the embeddings and to try to normalize them is applied. Otherwise, these methods are not able to converge and give lots of problems. So yeah, the first thing I want to show is that the results and how can we induce lexicons using heuristics. That is, the heuristics, these to and doc similarity of words. So what we want to do is to see that words with similar meaning have similar monolingual similarity distributions, that this red region and this green region is similar. To estimate the monolingual similarity, we just do a dot product of the embeddings. So that would be taking your embeddings in, let's say, English, that X, and do the product with the transport matrix. This is just the dot product between all word combination in a language. You want a distribution, so you assume that the distribution in the two languages is the same. This is the main assumption that we are taking here. So what we do is sort these dot products and then try to find similarity in this sorted list. And now what we have is the dictionary as the nearest neighbors again uses this this margin-based similarity between this X prime and Y prime. These spaces when you have just sorted the words according to this assumption that you are making about similarity. And the top words, you assume that they will be translations one of each other. The other big approach to do exactly the same is using adversarial learning to be able to get the dictionaries. In that case, what you are doing is trying to get the best projection matrix, the best W, using an adversarial network. Adversarial networks are quite intuitive, but they are really very difficult to convert. So this is why here also all the assumptions that you need to do on the embeddings and the cleanness and the normalization are very important. So what an adversarial network is trying to do is imagine that you have an input when you put into your system examples that are real and examples that you generate automatically. And you want a network that would be the discriminator, trying to guess which one is real and which one is fake. So which is the one that you are generating, and which is the one that comes from the real world. In our case of the embeddings, the real example would be your word in the target language, what I've been calling Y in the previous slide. And we will use this W matrix to generate fake examples. And you will train your system to try to be able to generate, to detect these real and fake examples. So you have two networks, you have this discriminator and this generator, you have two losses, one loss related to the generator and one loss related to the discriminator. And during training, you are trying to alternate from one loss to the other. So you are trying, the discriminator is trying to get every time better distinguishing between fake and real. And your generator is trying to get the W every time better, trying to generate really very good fake results. So at the same time, you are trying to distinguish real and fake, and you are trying to improve fake. So at the end, what you do is to get a very high quality W if you are getting the network properly trained. So sorry, again, where are we? So now we are trying to get these unsupervised cross-lingual embeddings. And as with the supervised embeddings, we have to start with, we have monolingual embeddings. And now we have this W that in this case we are learning with adversarial training. So this is, again, as before, our projection matrix for one space from the other. It turns out that this adversarial training is not that good and getting high quality Ws, but it's a very good way to initialize it. So what is done is that you use adversarial training for your phase iterations of your network. And then once you have something in W, you already know how to get W in another way, right? We know that it's the projection that you can solve with the procrustes problem. So they use the procrustes problem again to refine this W. So in this method, we have first an adversarial training, and then we have a refinement step. And now, again, the same thing that we were doing before. We use a margin-based similarity measure to be able to obtain the mapping between one language and the other, to obtain translations from the source language into the target language. How does these methods perform? So here is a comparison also taken from Mikel Artetx's thesis, when he shows the performance of this method that I've been talking about for the same languages that we have seen before. I will point more to the results for a very different language pair, English-Finnish here, the third column, and a very similar language pair, English-German here in the second column. What we have in the top rows are the results using 5,000 words as supervision. And these are some of the works that I described at the beginning for the supervised embeddings. Then we have the results that one can get only using 25 words. Then we have the results with these heuristics. Here is the example with the dog and the two, that heuristic of similarity of similarities. And then at the bottom of the table, we have the result with the purely unsupervised setting without any dictionary. What we see is that for 3 from the 4 languages, the unsupervised setting is better than any of the supervised settings. So we get accuracies close to 50% for closed languages. And only where the languages are very distant, English, Finnish, the supervised approach with a big dictionary is better than anyone else. So this Artetx et al. Is a supervision that uses 5,000 words for English, Finnish. And notice that the difference between 25 words and 5,000, it's not that big. So yeah, we have like 3-4 points of accuracy difference. And another thing I want to notice is that when we go to unsupervised system, this one here, we see a lot of zeros. And zeros means that the system is not converging. So this is one of the things that I was saying, that yes, these networks are very intuitive, are very nice, but they are very difficult to train. So in a lot of cases, the adversarial training simply does not converge. And this is what is happening with the unsupervised method by Kono and Lample, and a very one related, that this Zhang et al. And it's a void when you use embeddings and heuristics, like the one we have seen before, that when we use an embedding and an heuristic, the method is always able to convert. Okay, and we are close to the end of the session, and we have really done the hardest part of today, that was trying to understand cross-lingual embeddings. And I hope that now you really have a vision of how cross-lingual embeddings work, because they are really the main ingredient in unsupervised machine translation. If you have good unsupervised cross-lingual embeddings, you have good unsupervised machine translation. Otherwise, you have quite a deception in the results. So sometimes unsupervised machine translation does not converge either, because of the same reason of cross-lingual embeddings not converging. So let's go back to the first slide that I have given today. So we have done number 2, cross-lingual embeddings, and now the third part, it's really more simple to follow. And I will just start with the introduction, and we will finish in the next section, when only to give some hints here. So the things I'm going to talk about is just the 2 first seminal works. One is by this Isha group in Michel Artesi's thesis that was done, and all this work has been simultaneously done with Facebook with their own approach. So in both cases, both groups follow the same methodology. First, they have work on cross-lingual embeddings. This is Michel Arteche. Then they use these cross-lingual embeddings for learning unsupervised neural machine translation. And then they realized that the statistical components help a lot for unsupervised MP, and they did a statistical machine translation completely unsupervised and combined it with neural system. As I said, simultaneously, Facebook was doing the same. You see that the same year they have this paper on cross-lingual embeddings in a completely unsupervised way. The next step was trying to do unsupervised neural machine translation here. And then they also realized that the phrase-based and neural combination was the best thing to do for machine translation. So completely parallel path to get to the same way. What's the idea behind unsupervised machine translation? So yeah, the things we have been seeing. First, we have talked a lot about initialization. So unsupervised machine translation follows 3 principles according to Lampel and Kono and the Facebook team. And the three principles are initialization, denoising, and back translation. Initialization, we know what we do. We have these cross-lingual embeddings. What we are experts now on how to obtain good cross-lingual embeddings. So this is done. And then we have 2 more principles. One is denoising or language modeling, and as they call it in this paper, and the other one is back translation. So for denoising, the thing to do is we are in a monolingual setting. So what we can do is we can learn a very strong language model in one language, in the blue language here. We can learn a very strong language model on the other language, the red language here, and then try to learn good representations of the sentences by denoising. And we will see denoising next week. But here is represented by this plot here. When you have a sentence that you modify it a bit so that it's taken out of the language model corp. So you are adding noise to the sentence, and you are trying then to learn a network that knows how to take it back to the position. And you do the same in the 2 languages. So you do it in the blue languages, let's say English, and you do it in the red language, let's say Italian. And then finally, the third principle is back translation. So you are still in the monolingual setting, so you don't have parallel data. You don't know how to say that you are getting better in a translation setting without any parallel resource. So you go back to back translation. What does it mean? So let's assume that we have a sentence in the red language, Italian, and you use the current state of your system to translate it into your target language, let's say English. So now you have your English translation. So you still use your current state of the system to translate again this English sentence that has been artificially created to you into the original language again. So you have a new language into a new sentence into Italian. And now you can compare how different is your initial sentence that was really Italian and your back translation sentence into Italian again. And you want this difference to be as minimum as possible. So this is your loss function. You are trying to minimize this difference. You do this starting from Italian, and you do exactly the same starting from English. So you just have your English translation, use the current version of the model to go to the Italian one, go to the Italian to English again, and then in the English space, you can see how good or how bad is this translation. And this is the same thing, but looking at a specific architecture, not with the plots that we have seen before. All the architectures that are used for unsupervised machine translation in the neural setting are sequence-to-sequence architecture, of course, but then there are lots of variants. You can have a shared encoding between the two languages. In this case would be French-English. You can have a shared decoder that would be, again, French-English, or you can have two different decoders as in this experiment from Arteche, when you have a French decoder and an English decoder. In the supervised setting, you can also train a machine translation system this way. So in this supervised setting, you would have a French sentence here and input, that would be the input of your encoder, and you would have the equivalent sentence in English, that would be the equivalent of your decoder. But of course, this is not available in the unsupervised setting. What you need to do is to use the two principles for unsupervised machine translation, denoising and back translation. So what do you know for denoising? For denoising, for instance, you have in your encoder, you input your your French sentence in the encoder, and then your output is a noisy version of your input sentence. In this case, if we look at the sentence, the noise here implies changing the position of the word li. So, sorry, I'm not able to speak French, but in the source, you would have something like only fuselade or à l'aéroport. And in the target, you have the same, but li is later in the sentence. And this is what you give as input to train your system. And the task here is trying to learn these networks to convert your noisy sentence into the original one. So your loss function will try to minimize the difference between the noisy and the original sentence, both in English and in French in this case, in source and in the target language. The other example that we have in that plot was back translation. So you do exactly the same. You take your example, the sentence that you have in your input, the French sentence, and you use the current state of your system to get the English sentence. Now you have an English sentence, and you go to the encoder again and use the current state of the system to get the French system, to get the French sentence. And now what you do is the loss function is trying to minimize the difference between your English sentence and your translated English sentence. That would be this source to target here. And also would do the same for the other way around. So we're trying to minimize the difference between your French sentence and your translated French sentence. And the alternation of these two loss functions is that allows you to train an unsupervised neural machine translation. And it's very late, so I will finish with this table when we compare the results with these two methods that we have here, and I've been running too much. So we have here two language pairs with lots of resources, English, French, and English, German. These languages already get very high quality in a supervised setting because you really have lots of parallel settings, so parallel sentences. So you see two examples where a big transformer model was used in a supervised way, and translation quality as measured by Bleu is more than 40 for English, French, and more than 30 for English, German, so very good quality. We try to apply these two different methodologies, one by Arteche and the other one by Lampe and Conot. And we see that the best approach with only neural machine translation is getting something close to 25 for English French. That's 20 points below the state of the art of a supervised setting. But remember that we are not using any parallel data at all. So everything is done in an unsupervised way. And I said before that statistical machine translation was helping a lot. And you see that if you use a statistical machine translation and also you put together the neural components that we can see, you get closer to the supervised setting. You are still not as good as supervised machine translation, but you are closer. So we get like 36 for this 45 that we have in the supervised way, and we have 22 for this 33 that we have in the supervised setting. The question here is, if we really have so many data, why we want to do unsupervised machine translation? We really have lots of high quality parallel data. And this is a question that we will try to address in the next session. Finally, let me show you this last column here, because I've said that unsupervised neural machine translation can be done in two main blocks. In one block or approach would be via cross-lingual embeddings, and this is what we have seen today, and this is the results that show this table. But if you look at all the leaderboard for unsupervised machine translation, best quality translation for this language pairs specifically are not obtained with this cross-lingual embedding. So these huge multilingual models like GPT-3 or MAS, when adapted to the machine translation task, are able to be state-of-the-art for unsupervised machine translation. Still, the work that has been done by Artets et al., joining statistical machine translation and neural machine translation, is competitive, and for some test sets is still a state of the art nowadays. So this is a strong methodology for unsupervised settings. Okay, so we'll see the low resource setting next time. As you see, there are very few slides, so it's not going to take a lot of time. And next time we will combine this with another type of machine translation architecture that is not using parallel sentences. Still, we will leave machine translation in a supervised way from the end. So next time we will finish with unsupervised machine translation, and we will start talking about self-supervised machine translation for approaching the low resource setting. And very sorry for being late, but if you have any questions, I will still happy to answer them. And if not, I understand that it's already late. Sorry for that. The other option is that all of you already have a lunch in front of the computer. So yeah, then if we don't have any questions, I hope to see you in a couple of weeks. And we will try to talk a bit more about machine translation in the low resource setting.
Christina, maybe one question. The evaluation results you gave for the various tables, like for the similarity between the words and the multilingual embeddings, are they for the most frequent ones, or like for, like if you see a word only a few times, then the embeddings are not so good, and do people filter that, or?
You mean the tables when I give the performance comparing the two approaches? Yeah. There are a couple of test sets with embeddings, with a list of words for these parallel resources. So the Muse test set, and I think it's EPAL that it's called. There are two sets of words that are usually.
I see. Yeah. Okay.
And there is a combination. Most of the words are frequent words, but there are some rare words also.
Thank you.
Okay, so yeah, thank you everybody for staying till so late, and have a nice lunch, everyone.